Detailed explanations of upstream and downstream control of choke valves with respect to pressure control. Choke valves are critical components in the control of wellbore pressure and flow rates in oil and gas operations. Effective control of choke valves involves precise design, implementation, installation, and maintenance to ensure safe and efficient production. Here's a detailed explanation of the considerations for upstream and downstream control of choke valves. Pressure control through choke valves. 1. Upstream control. Objective: to maintain a stable pressure upstream of the choke valve, ensuring optimal flow rates and preventing reservoir damage. Implementation: use a feedback control system to adjust the choke valve position based on real-time upstream pressure readings. Pitfalls: rapid changes in upstream pressure can cause instability and oscillations if the control system is not properly tuned. Design considerations: ensure the choke valve has sufficient range and resolution to make fine adjustments. Choose materials resistant to corrosion and erosion. Operational concerns: monitor for hydrate formation and scale buildup that can affect valve performance. Implement real-time monitoring to detect and address issues promptly. Maintenance: regularly inspect and clean the valve to prevent clogging and ensure smooth operation. Schedule periodic calibration of sensors and actuators. 2. Downstream control. Objective: to maintain a stable pressure downstream of the choke valve, which is crucial for processing and transporting fluids. Implementation: use a feedback control system to adjust the choke valve based on downstream pressure readings. Pitfalls: downstream pressure fluctuations can impact flow stability and separation processes. Improper tuning can lead to valve hunting or instability. Design considerations: ensure the valve can handle the maximum expected pressure differential. Select materials that can withstand potential corrosion from produced fluids. Operational concerns: monitor for liquid slugs and gas blow-by that can affect downstream equipment. Implement safety measures to handle sudden pressure spikes. Maintenance: inspect the valve for wear and tear, particularly in high-pressure drop applications. Schedule maintenance during planned shutdowns to minimize impact on production. Detailed considerations. Design and implementation. 1. Valve selection. Type: choose the appropriate type of choke valve, e.g., fixed, adjustable, multi-orifice, based on the specific application and pressure control requirements. Sizing: correctly size the valve to handle the expected flow rates and pressure differentials. Oversized or undersized valves can lead to control issues. Materials: select materials that can withstand the corrosive and erosive nature of produced fluids. Common materials include stainless steel, Inconel, and Hastalloy. 2. Control system. Feedback loop. Implement a robust feedback loop with high-precision pressure sensors to provide real-time data to the control system. Actuators. Use reliable actuators that can precisely adjust the valve position. Pneumatic, hydraulic, or electric actuators can be used based on the application. Redundancy. Design redundant control systems to ensure reliability. Implement backup sensors and actuators to maintain control in case of primary system failure. Hatch installation 1. Location. Accessibility. Install the choke valve in an accessible location for easy maintenance and monitoring. Environmental protection. Ensure the valve is protected from harsh environmental conditions, such as extreme temperatures and corrosive atmospheres. 2. Mounting. Secure mounting. Ensure the valve is securely mounted to withstand vibrations and pressure fluctuations. Proper alignment. Properly align the valve with the piping system to prevent stress and potential leaks. Operations. Monitoring. Real-time data. Continuously monitor upstream and downstream pressures using high-precision sensors. Implement alarms for abnormal pressure variations. Data analysis. Analyze pressure data to identify trends and potential issues before they escalate. 2. Control adjustments. Tuning. Regularly tune the control system to ensure optimal performance. Adjust control parameters based on operational data. Response time. Ensure the control system can respond quickly to pressure changes to maintain stability. Maintenance 1. Regular inspection. Visual checks. Conduct regular visual inspections of the valve and associated components for signs of wear, corrosion, or damage. Performance testing. Periodically test the valve's performance to ensure it operates within specified parameters. 2. Preventive maintenance. Cleaning. Regularly clean the valve to remove debris and prevent clogging. Component replacement. Replace worn or damaged components such as seals and actuators to maintain reliability. Practical examples of issues and solutions. 1 issue: instability in upstream pressure control. Problem: rapid fluctuations in upstream pressure causing instability and oscillations. Solution: implement a control system with advanced tuning capabilities and fast response actuators. Use dampening techniques to smooth out pressure variations. 2. Issue: erosion of valve components. Problem: erosion of choke valve components due to high-velocity fluid and sand particles. Solution: select materials with high erosion resistance, such as tungsten carbide inserts. Implement sand management practices to reduce particle flow through the valve. 3. Issue: corrosion in sour service. Problem: corrosion of valve components in H2S environments leading to failure. Solution: use corrosion-resistant materials, such as Inconel or Hastalloy, and ensure compliance with AMR 0175 ISO 15156 standards. 4. Issue: data transmission failure. Problem: interruption in data transmission from downhole pressure sensors to the control system. Solution: use redundant communication paths and high-quality cables. Implement wireless telemetry systems where feasible to avoid cable issues. 5. Issue: slow response to pressure changes. Problem: slow response of the control system leading to pressure surges and instability. Solution: upgrade to high-speed actuators and improve the control algorithm to reduce response time. Implement predictive control strategies to anticipate pressure changes and adjust the valve position proactively. By considering these detailed aspects and implementing the suggested solutions, oil and gas operations can achieve effective and reliable control of choke valves, enhancing overall safety, efficiency, and production stability. Detailed design and selection criteria for choke valves. Choke valves are essential in oil and gas operations for controlling flow rates and pressures. Proper design and selection ensure reliable operation, safety, and efficiency. Below are the detailed design and selection criteria considering various aspects of the valve. Valve design. 1. Type of choke valve. Adjustable choke valves allows for manual or automated adjustment to control flow rates. Fixed choke valves, fixed orifice size, suitable for applications where flow rates remain constant. Positive choke valves uses replaceable beans or orifices to control flow rates in discrete steps. Cage choke valves, designed with internal cages to reduce noise and cavitation, offering precise control. 2. Flow characteristics, linear. Flow rate changes linearly with valve position. Equal percentage. Flow rate changes exponentially, suitable for applications with significant pressure variations. Quick opening provides maximum flow rate quickly, useful for emergency shutoff situations. Construction. 1. Body. Design. Robust and capable of withstanding high pressure and temperature conditions. Materials. Select based on the fluid characteristics, corrosiveness, erosiveness. Common materials include stainless steel, carbon steel, Inconel, and Hastalloy. Pressure rating. Ensure the body can handle the maximum operating pressure and potential pressure surges. 2. Bonnet. Design should provide a tight seal to prevent leaks. Bonnet types include bolted, welded, or pressure seal bonnets. Materials. Similar to the body, materials should resist corrosion and withstand operating conditions. Ease of maintenance. Designed for easy removal and reinstallation to facilitate maintenance. 3. Trim. Construction. The internal components, e.g. stem, seat, cage, that control flow should be designed for durability and precision. Materials must be resistant to erosion, corrosion, and high temperatures. Common materials include tungsten carbide, ceramic, and hardened stainless steel. Interchangeability. Modular trim designs allow for easy replacement and customization based on operating conditions. Hash materials of construction. 1. Body and bonnet. Carbon steel, suitable for non-corrosive environments. Stainless steel offers good corrosion resistance, suitable for mildly corrosive fluids. Inconel and Hastalloy, high corrosion resistance, ideal for sour service and highly corrosive fluids. 2. Trim components. Tungsten carbide, high hardness and erosion resistance, suitable for high velocity and abrasive fluids. Ceramic, excellent erosion resistance, used in highly abrasive environments. Hardened stainless steel provides a balance between corrosion resistance and durability. Maintainability. 1. Ease of maintenance. Modular design allows for easy disassembly, inspection, and replacement of components. Standardization. Use standardized components to simplify inventory and reduce downtime during maintenance. Seal design. Leak tightness. Ensure seals are designed to prevent leakage even under high-pressure conditions. Durability. Select seal materials that can withstand the operating environment without degradation. Instrumentation and control devices. 1. Actuators. Type. Choose between pneumatic, hydraulic, or electric actuators based on application requirements. Control. Ensure actuators can precisely control the valve position for accurate flow and pressure regulation. 2. Sensors. Pressure sensors. High-precision sensors to provide real-time pressure data upstream and downstream of the valve. Position sensors monitor valve position to ensure accurate control and feedback to the control system. 3. Control system integration. Ensure compatibility with existing control systems such as SCADA or DCS. Feedback loop. Implement a robust feedback loop to continuously adjust the valve position based on real-time data. Redundancy. Include redundant sensors and actuators to maintain control in case of primary system failure. Detailed considerations. Valve design. 1. Flow characteristics. Linear control provides a proportional flow rate to valve position, suitable for predictable flow control scenarios. Equal percentage, best for applications with varying differential pressures, ensuring smooth and predictable control. Quick opening, useful for emergency shutoffs, but less precise for normal flow control. 2. Orifice size, adjustability. Choose valves that allow for adjustable orifices for varying flow control needs. Sizing. Ensure orifice size matches the maximum and minimum flow requirements to avoid cavitation and ensure stable control. Construction. 1. Body and bonnet. Designed for strength. Bodies and bonnets must withstand the mechanical stresses from high pressures and temperature fluctuations. Material selection. Choose materials like carbon steel, stainless steel, or high-grade alloys based on the fluid properties and environmental conditions. 2. Trim components. Durability. Trim materials must resist wear, erosion, and corrosion. Tungsten carbide and hardened alloys are preferred for high abrasion environments. Interchangeable parts. Use standardized trim components to facilitate easy maintenance and replacement. Materials of construction. 1. Body and bonnet materials. Carbon steel. Economical and suitable for non-corrosive environments. Stainless steel offers good corrosion resistance for mildly corrosive applications. High-grade alloys, Inconel and Hastalloy, provide superior corrosion resistance for sour service and aggressive fluids. 2. Trim materials. Tungsten carbide, high hardness and erosion resistance, ideal for abrasive applications. Ceramic, excellent erosion resistance for highly abrasive environments. Hardened stainless steel provides a balance between corrosion resistance and durability for general use. Maintainability. 1. Modular design. Ease of disassembly. Modular components allow for quick disassembly, inspection, and replacement. Standardized parts. Using standardized parts reduces inventory complexity and downtime during maintenance. 2. Seal design. Leak prevention. Ensure seals are designed to prevent leaks under high pressure. Material durability. Choose seal materials that can withstand the specific operating environment without degrading. Instrumentation and control devices. 1. Actuators. Selection criteria. Choose actuators, pneumatic, hydraulic, electric, based on application requirements and control precision. Reliability. Ensure actuators provide reliable performance and can withstand the operating environment. 2. Sensors. Pressure and position sensors. High-precision sensors for accurate real-time data collection. Redundancy. Implement redundant sensors to ensure continuous operation in case of sensor failure. 3. Control systems. Compatibility. Ensure control systems are compatible with existing infrastructure, SCADA, DCS. Feedback mechanisms. Implement robust feedback mechanisms for real-time adjustments based on data. Redundancy. Include redundant control paths to maintain control during system failures. Practical examples and solutions. 1. Erosion of valve trim. Problem: high-velocity fluids causing erosion of valve trim. Solution: use tungsten carbide or ceramic trims for high erosion resistance. Implement flow conditioning devices to reduce fluid velocity and turbulence. 2. Corrosion in sour service. Problem: corrosion of valve components in H2S environments. Solution: use corrosion-resistant materials like Inconel or Hastelloy for body and trim. Ensure compliance with MR 0175's ISO 15156 standards. 3. Seal degradation. Problem: seal materials degrading under high temperature and pressure. Solution: choose high-performance seal materials like Viton or PTFE. Regularly inspect and replace seals to maintain leak-tight performance. 4. Data transmission failure. Failure in data transmission from sensors to control systems. Solution: use high-quality shielded cables and redundant communication paths. Implement wireless telemetry systems where feasible. 5. Actuator malfunction. Problem: actuator failure leading to loss of valve control. Solution: use reliable, high-performance actuators with regular maintenance schedules. Implement redundant actuators and manual override options. By considering these detailed design and selection criteria, along with practical solutions for common issues, oil and gas operations can ensure reliable and efficient performance of choke valves, enhancing overall safety and productivity. Explanation of various types of choke valve control used practically in various installations. Choke valves are integral to managing the flow of fluids in oil and gas operations. Different types of choke valve controls are employed based on specific operational requirements. Here are explanations and practical examples of various kinds of choke valve controls, along with their advantages and disadvantages. 1. Manual choke valves. Example: used in simple, low-pressure applications where fine control over flow is not critical. Advantages: simplicity, easy to operate with minimal training. Cost-effective, lower initial cost and minimal maintenance requirements. Reliability: fewer moving parts and no need for external power sources. Disadvantages: limited control, requires manual adjustment, which can be time-consuming and imprecise. Operational delay: not suitable for applications requiring rapid adjustments. Safety risks: manual operation in hazardous environments poses safety risks to personnel. 2. Pneumatic choke valves. Example: commonly used in offshore platforms where remote control and quick adjustments are necessary. Advantages: fast response, quick adjustment capabilities for changing operational conditions. Remote control can be operated from a distance, enhancing safety and convenience. Reliability: pneumatic systems are generally reliable and can function in a wide range of environmental conditions. Disadvantages: complexity, requires a compressed air system, adding to the complexity and cost. Maintenance, requires regular maintenance to ensure the air system is free of leaks and contaminants. Dependency on air supply, loss of air supply, can lead to loss of control. Hydraulic choke valves. Example: used in deep-water drilling operations where high precision and control are necessary. Advantages: precision control, provides precise control over valve position, ideal for high pressure and critical applications. High force capability, can handle high pressure and heavy-duty operations. Remote operation, allows for remote control, improving safety and operational efficiency. Disadvantages: complexity and cost, more complex and expensive to install and maintain than manual and pneumatic systems. Potential leaks. Hydraulic systems are prone to leaks, which can be costly and environmentally hazardous. Maintenance, requires regular maintenance to ensure system integrity and performance. 4. Electric choke valves. Example: used in automated production facilities where integration with digital control systems is required. Advantages: easily integrated with digital control systems, e.g. SCADA, DCS, for automated control. Precision, provides accurate control over valve position. Remote operation, facilitates remote operation and monitoring. Disadvantages: power dependency, requires a reliable power supply, which can be a limitation in remote locations. Complexity, more complex to install and maintain compared to manual and pneumatic systems. Initial cost, higher initial costs due to advanced components and installation requirements. 5. Fixed choke valves. Example, used in stable flow applications where flow rates do not need frequent adjustment. Advantages: simplicity, simple design with no moving parts, reducing maintenance needs. Reliability, high reliability due to the absence of adjustable components. Cost-effective, lower cost due to the simplicity of the design. Disadvantages: inflexibility, flow rates cannot be adjusted once installed, limiting operational flexibility. Not suitable for variable flow, ineffective for applications requiring frequent flow adjustments. 6. Positive choke valves. Example, used in well testing operations where discrete flow rates are required. Advantages: precision, provides precise control over flow rates using replaceable orifices. Simplicity, simple to operate and maintain. Cost-effective, lower cost compared to adjustable choke valves. Disadvantages: manual adjustment, requires manual replacement of orifices to change flow rates. Operational downtime, changing orifices can cause downtime and interrupt operations. 7. Cage choke valves. Example, used in high-pressure gas lift operations to control gas injection rates. Advantages: noise reduction, designed to reduce noise and vibration, ideal for high-pressure gas applications. Cavitation control, effective at controlling cavitation and erosion. Precision, provides precise flow control with minimal wear and tear. Disadvantages: complexity, more complex design, making maintenance and repairs more challenging. Cost, higher initial costs due to advanced materials and construction. Specialized applications, best suited for specific applications, limiting general use. Practical examples and their limitations. 1. Offshore platform control, type pneumatic choke valves. Scenario, an offshore platform requiring quick adjustments to manage well pressure due to changing sea conditions. Advantage: quick response time and remote control capabilities enhance safety and operational efficiency. Disadvantage: the need for a reliable compressed air system adds complexity and maintenance requirements. 2. Deep water drilling. Type hydraulic choke valves. Scenario: high-pressure deep water drilling operations where precise control is crucial. Advantage: high precision and control over valve operations improve safety and efficiency. Disadvantage: high complexity and potential for hydraulic fluid leaks increase maintenance demands. 3. Automated production facility choke valves. Scenario: an onshore production facility integrated with digital control systems. Advantage: seamless integration with SCADA systems allows for automated and remote control. Disadvantage: dependency on a stable power supply can be a limitation in areas with unreliable electricity. 4. Stable flow applications. Type fixed choke valves. Scenario: applications with stable flow rates, such as long-term production wells. Advantage: high reliability and low maintenance due to the simplicity of the design. Disadvantage: lack of flexibility in adjusting flow rates limits operational adaptability. 5. Well testing operations. Type positive choke valves. Scenario: well testing where precise, discrete flow rates are needed. Advantage: precise control over flow rates enhances the accuracy of test results. Disadvantage: manual adjustment of orifices can cause operational downtime. The selection of choke valve control types depends on specific operational needs, including the required level of control precision, environmental conditions, and maintenance capabilities. Understanding the advantages and disadvantages of each type helps in making informed decisions to optimize performance, safety, and efficiency in various installations.